Hi, I'm Ye Wang. Welcome to the audio slides of our recent work regarding to the coloring of aluminum surface by anodization. Aluminum products have been widely used in our daily life. But have you think about how to color the aluminum surface with those brilliant colors? In this paper, we present an environment-friendly method to coat the aluminum surface with a nanoporous alumina layer, and this alumina layer have intrinsic vivid color without using any toxic dyes. We also find out that the purity of aluminum have huge impact to the process of coloration. Now let's have a brief overview of the conventional method of aluminum coloring. As you know, natural aluminum doesn't have brilliant color. To color aluminum, people use a technique called anodization to create a porous oxide layer on the top of aluminum. As shown in step 1, anodization is conducted by passing direct current through electrolyte solution, where aluminum is used as anode. During anodization, the oxygen ions driven by the current will move to the anode to oxidize the surface into alumina. At the same time, a self-assembled nanopores will form on the alumina film as shown in step 2. After anodization, the metallic salts or chemical compounds will be deposited into the nanopores of oxide layer to produce a light-resistant color. However, the chemicals used for coloring are toxic to human and environment. In contrast to this method, in our work, we use a technique called pulse anodization to color aluminum surface. As you see on the right of the slides, the resulted aluminum surface have very brilliant color and natural white light. The reason why this kind of alumina coating can have color is because our pulse anodization technique can create a stacked layered nanostructure on the anodic alumina film, which engineer the surface into a kind of photonic crystal to selectively reflect light at a certain wavelength. As you see from the SM image, the stack layered nanostructures are formed after pulse anodization. The thickness of stack layered structure are controlled by the parameter of pulse anodization. The color of the aluminum surface actually comes from the interference light rays that bounce from the bottom and the top of the layer. The thickness of the layer determines how those two rays interfere. For each thickness of oxide layer, some light rays of specific colors can be exactly a half wavelength out of phase. So when they recombine at the surface, they cancel each other, and thus we can't see those colors. Only in-phase light rays can show their colors, and each stack layer can be treated as a mirror to enhance the reflected light at a certain wavelength. In a word, the stack layered nanostructure that we engineered on the surface can selectively reflect light rays that are in phase inside nanopores. The color of reflection can be controlled by the thickness of the layer. What is interesting is that the purity of aluminum can influence the color of coating. With the same coating condition, the color of coating on high purity and technical grade aluminum is different. To understand why aluminum purity can influence the color coating, we analyzed the electrochemical data during anodization. Although the conditions that we applied for anodization are the same for both experiments, the growth rate of anodic alumina is different. We found that the growth rate of oxide layer in high purity aluminum is higher than that in technical grade aluminum, as shown in table and figures. As we discussed before, the thickness of the oxide layer determines the interference rays that bounce from the bottom and the top of the oxide layer. Therefore, the difference of stack layer thickness on high purity and technical grade aluminum makes the final coating have different color. We also analyzed the structural difference of anodic alumina formed on high purity and technical grade aluminum. As shown on the left of the slide, we found that high purity aluminum have flat surface while technical grade aluminum have rough surface. On the right of the slide, we show that anodic alumina layer in high purity group are uniform. However, the oxide layer formed on technical grade aluminum have defects and holes. This effect is related with the metallic impurities in the aluminum substrate. This kind of structural difference of anodic alumina layer also have impacts of the color coating. In summary, in this work, we developed an environmental-friendly approach to color aluminum by pulse anodization. We analyzed the difference of color coating in high purity and technical grade aluminum. Our technique can be an alternative method for color coating in metal finish industry. We also have other interesting works related with photonic coatings of aluminum surface by pulse anodization. Please feel free to check them online. Thank you for listening. I'm Ye Wang.